here. So we end up at this step in the last page. Now we want to simplify this again to simplify this two summation further. So the term in the first summation is xr plus n, while in the second summation is xr plus n plus 1. So we need to replace switch the summation index so that the second summation, the power of x is also r plus n. So that can be done by when n is 0, the first term is n is 0. When n is 0, this is xr plus 1. So we let n plus 1 to be k. N plus or in this way, n plus 1 to be a new n. Then the original n is the new n minus 1, and the new n run from 1 to infinity. Okay, so we copy the first summation here without change, and then we replace the n in the second summation by n plus 1. So this will give us n from 1 to infinity, a n minus 1 xr plus n. These two summations are the same. When n is 1, this is a0 xr plus xr. Sorry, yeah. N is 1 corresponding to this n equal to 0. Okay, so you need to convince yourself that these two summations are the same. Just replace the n in the first summation by n plus n plus 1. So when n is 0, correspondingly the new n is 1. Okay, and the other n corresponding to the change. Okay, this is very fundamental, very easy. I believe you can deal with this. Okay, so we have two summations. The power of x in these two summations are the same. So these two summations can be combined. But the range of n in the first summation is from n from 0, and the second summation is n from 1. So the first summation has an extra term corresponding to n equal to 0. So to combine these two summations, we need to write the term corresponding to n equal to 0 separately. Okay, so the first summation, we write the term corresponding to n equal to 0. N equal to 0, that is 2a0 r, that is r. Then r plus n minus 1 is r minus 1. Minus r plus 1, we move the an out, which draw the an out together. So x to the power r. Okay, this is the term in the first summation corresponding to n equal to 0. Then having written the term corresponding to n equal to 0 separately, this summation becomes n from 1 to infinity, so that it can be combined with the second summation. Okay, so this is n from 1 to infinity. We copy the coefficients of the first summation, that is here. Then add the coefficient of the second summation, a n minus 1. And then all this multiplied the common xr plus n. Okay? So this is the computation. This is the computation of substituting our y prime and y double prime to the equation. So substituting y prime, y double prime to the equation, the left hand side is 0. The right hand side we compute the bala a long computation. We end up at this. So this last result, the final result must be 0. Therefore, every term must be 0. Because every term or every coefficient of the power of x must be 0. So 2r r minus 1 minus r plus 1 must be 0. Okay, this must be 0. A0 you don't need to you don't ask A0 to be 0. Okay, because A0 only affect the multiply of y, but our equation is a homogeneous equation. If y is a solution, the multiplication of y by a real number is also a solution. So without loss of generality, we can assume that the first coefficient A0 is 1. So you don't want to consider A0 to be 0. Okay, so A0 is not 0. The R have to satisfy this equation. This equation is called integral equation. And the solution, the root of this equation are called exponents at the singularity. Solving this equation will obtain the two roots, which are the so-called exponents at the singularity, which is R1 is 1, R2 is a half. So for every R1 and R2, we determine the AN. For R equal to R1, we determine the corresponding AN using this coefficient to be 0. The coefficient in the summation are all 0. Therefore, using R1 to be 1, we require this to be 0. This can be simplified. Simplified is this. So how to simplify? The first three term has an OAN. We take the common AN out and compute simplify the remaining coefficients. And then this is this. Okay, and then plus the AN minus 1 is 0. Okay, so we need to, for R equal to 1 and R equal to a half, using this recurrence relation to determine the corresponding AN. Having determined R and AN, you obtain the solution of our ODE. Okay, so we need to go to next page again. So I will also copy this to the next page. That is here. Okay, now we determine the AN. Using this recurrency relation, we can express AN using AN minus 1. That is here. Okay, AN is divided the coefficient of AN, and we have a negative sign here because I move AN minus 1 to the right hand side. And then to simplify it, I factoring the denominator. By a simple elementary computation, you can factoring this denominator to be the multiplication of these two terms. Okay, so this is the recurrency relation, which AN minus 1 and AN. Now we determine the AN for R equal to 1. For R equal to 1, this recurrence relation becomes this. When R equal to 1, this relation is looks much better. Okay, so using this relation, we can determine the A1, A2, and so on. Because our AN is from 1 up, right? Our AN here is from n equal to 1. Of course, n equal to 1, the last coefficient is A0. A0 we can choose arbitrarily, and every term will be expressed using A0. Okay, so A1, when n equal to 1, A1 is minus A0 over 3 multiply 1. Okay, and then A2 is negative A1 over, when n equal to 2, the denominator is 5 multiply 2. But we already have A1, so we need to compute further to express A2 using A0 also. That is A0, 3, 5, 1, 2. Okay, and then step by step, A3 is minus A2, 7 and 3. And then we replace the A2 by the expression using A0. We will see that A3 is minus A0 over this multiplication. Again and again, eventually we obtain that an is minus 1 to the power n a0, and the multiplication of the odd number 1, 5, 3, 5, 7, and finally 2n plus 1, and then 1, 2, 3 until n. Therefore, we get n here. Okay, this is the expression of an. This an can be simplified can be written in a better form. How to say? We multiply both sides by 2, 2 to the power n. This 1, 2, 3 until n, every term multiplied by 2, we get 2, 4, 6, 8. And the 2, 4, 6, 8 until 2n, multiplying which is 3, 5, 7 until 2n plus 1, give us 2n plus 1. 2n plus 1. Okay, so our an has this very elegant expression. Therefore, the corresponding solution, so having computing an, we already can write down the solution. But before writing the solution, we can, using the coefficient an to determine the radius of convergence of the solution. So, the radius of convergence is the limit of an over an plus 1. If this limit is if this limit exists, then the limit is the radius of convergence. So this substituting the an and the an plus 1 inside and simplified this expression is 2n plus 3 over 2, and as you can see, the limit is infinity. This means that the radius of convergence is infinity. Therefore, this means the power series is convergence for all x. Okay, so our solution is y1 is x 1 plus this. Okay, we assume a0 is 1. Okay, we assume a0 is 1. So our power series is this. Of course, if a0 is not 1, every term contain an a0. The corresponding solution is precisely multiplication of our solution. So as I said, because the equation is homogeneous, this is essentially the same as with a0 equal to 1, just the multiplication. Okay. So this solution, let's have a look on this solution. This solution is analytic, right? X is analytic, and this is also analytic. Therefore, the multiplication is analytic. Or you can see this way. Multiplying x inside, this is x plus sigma to the x n plus 1, x to the power n plus 1. So this y1 can be expressed by convergence power series. Therefore, it is analytic. Okay, but for our r equal to a half, we determine this solution for r equal to 1. R equal to 1, this is y. Okay, look, our solution is y equal to xr sigma an xn. So when r equal to 1, our previous computation is for r equal to 1. Therefore, the power of x here is 1. Okay, compare. Our solution is xr sigma an xn. When r equal to 1, this is y is x sigma n from 0 to infinity an xn. So when n equal to 0, a0 x, we take a0 to be 1. R is 1. So this gives us the solution here. This solution is analytic. But for r equal to a half, using similar computation, it is tedious and long, and I will not repeat it here. And if you like, you can check the textbook. So when r equal to a half, you can also find the coefficient an. You can also find the coefficient an here. Okay, then using that coefficient an, you can construct a power series. The power series multiplied x to the power a half give you the other solution. Okay, so the solution look like this. r equal to a half, therefore the power over this r is a half. Then this is the power series for r equal to a half. Okay, so we use r equal to 1. We use r equal to 1 to determine the an and obtain this solution, right? But we can also use r equal to a half to determine the an similarly and obtain another solution, another power coefficient of power series. But this power series need to multiply r to the power 1 over 2 to get the solution. Because the form of the solution, our form of the solution is xr summation. Xr multiply the power series. Okay. Anyway, we have obtained two solutions of our equation, and these two solutions are not linearly dependent. They are linearly independent. Okay. Therefore, they are the fundamental solutions of our equation, and their linear combination is the general solutions. Okay.